Assalamu alaikum. Hi everyone. In this video, I would like to demonstrate how to construct a Matlab program for solving transient problems in switch mode RLC circuits using the fourth order Runge Kutta method, or normally known as the RK4. So the circuit response is determined by an ordinary differential equations, or in short we call that as ODE, or it can also be determined by a set of ODE that can be more than one equation. So here I bring in three examples. That is, the first example is related to an RC circuit that results in a single first order ODE. Second example is related to an RLC circuit that provides two first order ODE that looks like a set of simultaneous equations. And finally, example number 3, which refers to the same circuit as in example number 2, but the governing equation is in the form of a single second order ODE. So let's begin with the first example. So in here we need to solve the voltage across the capacitor known as small v using RK4. So all the values for the elements are given here, R and then C. And this is a DC voltage source that has a constant value, of course. So given the initial voltage across the capacitor as 0, and we want to solve it over the interval t from 0 to 1 using the RK4. So one of the first steps that need to be done is the ODE, the ordinary differential equation, must be presented in a regular form like this, in which only the derivative term is left at the left-hand side of the equation, and we bring the others to the right-hand side. So the terms at the right-hand side is assigned with a function, for example, this f function of t, v. So notice that variable t is not present on the right-hand side, so we can also call the function in this particular case as fv. By the way, we make it general because in some cases vs, which is the voltage source, can be a function of time like the ramp function or sinusoid or others. And here is the main equation of the RK4 that describes the next value of V based on its present value, and K1 until K4 is the quantities that need to be used to compute Vi plus 1. All right, let's begin with the programming. So I already opened the blank script to write the code. Okay, so we begin with example number 1. So let's put some header here. And then I normally begin my script with clear and CLC. So we can already list all the constants value. So R is 2 kilo, C equals to 50 micro, and the voltage source is 12. And then we know that the end time for the simulation is 1 second, so let's write Tn equals to 1. And then we have to decide how many steps or how many sub-interval that we wish to use. So let's call that small n equals to 50 that describes the number of steps. And then we have the step size, which is obviously equals to Tn. So we call that h equals to Tn divided by small n. And we can generate the array for the time for t, in which t is from 0 with the step size h until Tn. What else? I think we can already describe the function ftv. So let's use the let's use the function handle. So f equals to f is a function of t and v, in which f equals to -1 over rc times v, or maybe we can write -v divided by r times c plus vs divided by r times c. Okay, be careful with the braces. And then we can begin to write the program for the Runge Kutta formulation. And we should begin with defining the initial, sorry, I hit enter at the wrong window. We have to define the initial value for the voltage. So given V at time 0 equals to 0. So in here, we wish to have an array for V. So the first value in the array is the initial value of the voltage. So we write V bracket 1, meaning that the first elements in the array equals to 0. Okay, now we can already describe the RK4 formulations. So we construct a for loop for that purpose. I starting from 1 until small n, and we have to describe this K1, K2, K3, K4 first before defining Vi plus 1, because Vi plus 1 relies or depends on K1 until K4. So K1 is H times F. So T I, okay, T bracket I. So T is also the array Vi. So that is K1. So then we define K2. So I copy K1 and paste it here. So Ti plus H over 2 Vi plus K1 over 2. Then K3. Okay, here it should be K2 over 2. And finally K4. K4 equals to H times F Ti plus H Vi plus K3. And then we write the main equation, which is Vi plus 1 equals to Vi plus 1 over 6 times K1 plus 2, K2 plus 2 times K3 plus K4. And we close this with end. So let's double check everything before we run the script. Okay, so F T here, Vi here plus K1, K2, K3, H over 2, H, and I think everything is correct. So we can already run our program and check the workspace. So let's name this as RK for example. Save this. And if you inspect your workspace, you can find that the array for V and T have been generated. If you want to present the data for T and V in a table-like manner, you can use the fprintf command inside your script, or you can simply write on the command window square bracket T transpose space V transpose, close the bracket and hit enter, and you can display already the data for T and V. By the way, uh, normally we wish to see the graphical representation of the response, so we can um, construct a figure. So write figure here. So since we have 3 examples, so let's call this figure number 1. And then we plot T, comma V, and let use the mark X to indicate the points. And then we label the x-axis. For example, T unit is second, and also the y-axis is the voltage, V unit volts, and we can rerun our program. So this is the voltage response of the capacitor, of the voltage across capacitor, in which the cross indicates the position of the values, in a discrete way. If you want to have like a continuous graph, you can remove this cross X, and then you rerun your program and you get like a continuous graph. But bear in mind that this is actually a discrete function. Okay, so let's continue with example number 2. So example number 2 comprise a set of ordinary differential equations. Here we have 2 equations. The first equation corresponds to dV over dt, the voltage across the capacitor, and equation number 2 corresponds to the current through the inductor. So by using the KCL and KVL, you can derive these 2 equations. And similarly, we have to solve this set of equation within 0 to 1 interval, and given here the initial voltage 0 and the initial current 0 as well. And here we have the elements of the inductor L given as 10 Henry. So let's begin with the program. Let me have some space down here, and we begin it at this line. So put some command to start the example number 2. So since we already have some value in the workspace, I think we should clear some of them, which is the function f, and then the array v, and all the k's, k1, k2, k3, and k4. So if we highlight this line and evaluate it, so we can remove all the values, the variables from the previous example. Okay, so let's continue. So now we have additional constant, which is the inductor equals to 10. Then we can begin the RK formulation. So in the previous example, we have the function f. Now we have 2 functions. Let's call the first function as f and the second function as g. So this is t, function of v, and also this time function of the current I. But I don't like to use I for other variables, because I normally use for the index, like this one for I until 1 until n. So let's use other symbol to indicate the current. Let's say Q maybe. So this equals to negative V over RC plus I over C, so Q over C. And then G, the function corresponds to the second equation, is also the function of T, V, and Q. Sorry, copy this, paste it down here. So negative V over L plus Vs over L. Okay, again, in here, we don't have the term T appears on the right hand side of the equation. By the way, we make it general because in some cases, again, Vs can be function of time. Okay, so let's proceed. So the initial voltage given as 0 and also the initial current as well is 0. Then we can have this Runge Kutta formulation. So maybe we can copy from the previous example and paste it down here. So now we have two sets of K, K1 until K4 for V, and also the same thing for I. But we have to use a different notation. So for the current, we use L, So focus on the set of the equation on the slide. So let's take K2. Okay, notice that K2 depends on L1. L2 depends on K1 here. So we need to be smart how to arrange this set of equations. But before that, K1 must be modified by including Q inside the as the arguments for K. And then after K1, we have to declare L1 first because K2 will require the information of L1. So this is L1 H time G, okay? And then K2 comma Qi plus L1 over 2, okay? And then L2 is this time G, and proceed K3 comma Qi plus L 2 over 2, and then we copy this to have the equation for L3. So L3 is H times G, and finally K4 comma Qi plus L3 and L4 is H times G. Okay, so the equation for Vi plus 1 is just the same, but we have to add the equation for Qi plus 1 as well, which equals to or maybe we just rewrite everything. Qi plus 1 equals to Qi. Okay, remember that the current or Q is related with the L1 plus 2 L2 plus 2 L3 plus L4. Okay, let's rerun this program and see what do we have. So here in the workspace we have the response for Q and also V. Okay, again, if you want to present that in the table like presentation, you can write V T transpose spacing V transpose spacing Q transpose, and then hit enter. So you have 3 columns, like a table. So the second column corresponds to V, and the third column corresponds to Q. And we can plot the graph for V and I, or V and Q. Okay, sorry, I miscopy copy that, copy and paste here. And so figure 2, okay, since here we have two graph, so we can use subplot to plot that. Okay, so figure 2, so first we subplot. So let's arrange that like a 2 by 1 matrix. So 2, 1. So the first plot is V, and then we label that. And the second plot on the subplot is the current Q. So the current, we label that as A with unit, sorry, I with unit A. So if we highlight this and right click, evaluate selection, we have the response for the voltage and the current. Okay, if you inspect this graph, it looks not really smooth, The reason is because the number of steps that we use is relatively low. If you wish to see the like a smooth graph, you can increase this maybe to 1000, so the step size now become 1 milliseconds. You rerun everything, so you get a nice looking smooth graph. Okay, but remember again, the response is not continuous because we are using numerical method, so it gives something like a discrete value. Okay, so okay, if you notice this set of equation, K1 L1, K2 L2, K3 L3, K4 L4, it can be written in a concise manner. But we have to know how to use uh, the vector, the concept of vector, to utilize the vector. So for that purpose, we can write a function handle that consists of two functions, f and g. So first, let us comment this and write big F. Now big F is a function that consists of two elements, which is small f and small g. So big F is the function of t, v, and q, but this time it is a matrix. So the first element of the function is f, small f, and the second element of the big F is g. Okay, so we separate it with the semicolon. Then we want to replace this small k1, small l1, k2, l2, and so on with a single, single k. So for that purpose, let's copy this for loop, and then we comment it because we wish to use another style. So first we remove L, okay, and then we change the small k with the big K. So K2, big K3, and big K4. And now remember that there is no more small f and small g because the function has been replaced with big F. So we multiply this with big F here, and that's this small k, k1 over 2 that corresponds to v, must be replaced with the big K, I mean the first element of big K, so k1 bracket 1, and L1 must be replaced with the big K1 bracket 2. Okay, so this is K2 bracket 1 that corresponds to voltage. I have extra this, and this should be K2 2, and this one is K3 1, this is K3 2, and so Vi plus 1, okay, so we have to change this to K1 1, 1, plus 2k, big K 2, 2, the big K 3, sorry, 1, okay, my mistake. So 1 and also big K1. Again, the first element in the big K corresponds to the voltage, and the second element in the big K corresponds to the current. So maybe we can just copy this and change the index here to 2. Okay, so now let's rerun our program. And here we get the graph, the response, that exactly the same with the one that we had from the previous technique. Okay, so let's proceed with the third example. So the third example is a little bit tricky because it corresponds to the second order ordinary differential equations. All right, so for that purpose, we must reduce this second order equation to a first order equations. You know, every time when we face a higher order ordinary differential equation, we need to reduce it to the first order equations. But I don't want to tell the derivation in detail. By the way, in short, this equation, you know, can be replaced by this set of equations comprises small v and small z. So z in here is actually the first derivative of the voltage. So the first derivative of z becomes the second derivative of the voltage, d squared v over dt squared, in which we can have d squared v over dt squared equals to everything on the left hand side except that term. We bring that to the right hand side. So that becomes the terms that appears in the second equation. So now we have a set of first order ODE, you know, which has the similarity with the previous example. So we call the term on the right hand side in equation 1 as f, and the term on the right hand side for equation 2 as small g, you know, small f and small g. And nothing much to be done here. Actually, we can copy the coding from example number 2. So first, maybe we can remove all these unrelated lines. Okay, now we are ready to construct for example number 3. So change this to 3. Okay, now we have to clear a few lines, a few variables, small f, small g, v, and then q, and all the big K. Okay, and we don't require L because it's already declared up there. Now our functions for big F is simply this Z, but before that, now F is the function of t, v, and z. Remember again, z is the first derivative of v, and we change this part to negative. Maybe we just modify a little bit things here. So this LC, and then minus Z over RC, and plus VS over LC. Okay, let's double check everything. Okay, minus this and plus this. This is RC. Okay, and then we have V1 and Z1. And we change all of this to Z. Okay, what else that we need? And I think that's already done for this part. And let's run first and see what do we have on the command window. Hopefully no error. Okay, so to get the graph for the third example, we can copy this and create figure number 3. So here we have the, instead of Q, we need to plot Z. So Z is not the current. Z is actually the first derivative of the voltage. So the unit is volt per second. Okay, so rerun everything. Okay, so let's compare figure 2 and figure 3. So the voltage response should be exactly the same because they comes from the same problem. But the second graph in here on the right hand side, it is actually the response of the first derivative of the voltage. So to get the currents, we can use some circuit analysis here. So the current through the inductor equals to the current through the capacitor plus the current through the resistor. So we can write something like, so based on this finding, V and Z, so we can get the current equals to, the current of the inductor equals to the current through the capacitor, which is C times Z, plus the current through the resistor, which is V over R. Okay, again, the current through inductor equals to the current through the capacitor plus the current through the resistor. That is KCL. And then to plot that, maybe we have to have another subplot here. So change this to 3, 3, and then copy these lines, paste it here. So we have the third graph that show the plot for the currents Q. So this should be the current I with unit A. So let's rerun everything again. And here, let's compare figure number 3 and figure 2. Okay. So the voltage again are the same, and then let's inspect the currents. Okay, the third graph on the right hand side is the currents, which are identical with the second graph on the left hand side, coming from the example number 2. All right, so I think that's all for the demonstrations. So thanks for watching. See you next time.